Now, last class, my slides got jammed up and they stopped presenting, but we'll see if they work this time. And so let me just sort of move you over there, Dora. Always got to have a picture of Dora. That but this isn't a recent one. Well, it's from last fall, and it's again the Northwest Arm in Halifax. That it was a beautiful morning in the fall when end of October, maybe beginning of November, something like that, end of October. That so right now I'm not in Halifax. I'm down in Kingsburg, down on the South Shore, past Lunenburg. And this morning at sunrise, this is what it looked like. It was really, really pretty. Except if you know the expression, red sky in the morning, sailor take warning. Red sky in the morning means you've got a storm coming. And we're expecting it to hit down here anytime. And it's supposed to be a mix of snow and rain before changing to rain. Yeah, yuck. But tomorrow is supposed to be sunny again, but incredibly cold. I hope you enjoyed yesterday. Yesterday was a beautiful day. So we were outdoor and I walking, and this is Kingsburg Beach, not far from where we are, and sort of down the road, and looking across from Rosehead side over to the Hell, it's called, yeah, Hell. It's got all kinds of rocks and shoals around it, so it's a dangerous spot. But there's this field where often you'll see a few deer, sometimes four, sometimes six. I've seen up to about 12, and there were about 20 there yesterday afternoon. It was quite the sight. They were all just sort of staring at me, and they have their funny little ears, and they stare at you. Anyway, there's one of them. Another one staring at me. These guys staring. The others hadn't noticed yet. Oh well. So let's get on to get some work done. Yeah, let me slide this over. So, um, a few updates on things. Uh, One student emailed me after the test on Friday, or when he got the results Saturday, and saying, you know, um, I got 14 out of 16, but what did I get wrong? And this student's one that does very well in the course. So I looked it up, and it was question 6 and question 7 that he got wrong. And they were both scatter charts. And if you recall the two scatter charts, one of them was a scatter that, question 6, it actually had a bit of a trend going up. It's got a correlation of around 0.2, 0.3, thereabouts. Uh, and so the correct answer was a weakly positive relationship. But he thought there was no correlation. He didn't see the pattern that was there. And question 7 was a scatter that sort of went downhill, and that um, that most students were picking a weakly negative correlation. It was around 0.5 or zero point 0.6 is the correlation. So I'd say it's moderate correlation there. But then it struck me that because so many people were falling into picking exactly the same answers he was, unless you've got a lot of experience with scatter charts and correlations, you may not be able to distinguish those things very well at all. You might be able to see a little bit, and you can see a really strong correlation, sure. But weak ones, moderate ones are actually very hard to deal with. And I've probably told you that it's correlation is surprising at times. That we saw it with income, where it was okay. There's a bit of an upward slope to it. It had a correlation of around 0.46. So anyway, nice thing is I could go back into Top Hat, and I've accepted both answers. So so now for those two questions, there are two answers that are classed as right answers. And so if you had looked at your grades on Saturday and you looked at your grades last night or since last night, you'd see that they've changed because I've changed the what's right, what's wrong. So the average grade is actually quite good. It's up over 13, I think. Out of 16, that's pretty high. So we got some good results. Um, final exam? What final exam? There's no final exam. I know we're conditioned to think there's always a final exam. And um, I've decided I don't want final exams anymore. This regular testing is giving me, people are working really hard, you're studying hard, you're learning the material. I don't think a final exam would accomplish anything except put you under additional stress. And that I started moving this way because of actually a year ago, because of just seeing the stress I was seeing students increasingly getting under uh, with finals. And did we really need to do that? Because what I was grading and evaluating was your ability to do well under stress, as opposed to do you understand the material? And they're different. Um, that and I don't care about. Not my job to do a stress test on you. And with COVID, I moved even further in that direction of getting rid of that type of thing. And I, so far, I haven't seen any reason why I should ever go back to having finals. So a couple other things. Uh, Still, I'm missing students doing tests and quizzes. And in the past, I've gone and emailed everybody. I'll probably be sending out an email about this after class because most of you aren't on the call. Um, but if you do miss things, that and things happen, and I've got you doing an awful lot of little activities during the term. If you miss something, email me and we'll work it out. That, or if you're running into difficulties, we had one that contacted me Sunday morning that had started the quiz and was halfway through it, and then something came up and he had to leave the quiz. And by the time he was able to get back to it again, it was after 11 o'clock or whatever, and it had closed. And uh, so we worked out something, and I can usually find solutions, but you have to ask. Um, Assignment 3 is posted. It's all on multiple regression. Well, that and a little bit of box and whisker. And so it's an Excel-based assignment again. And I expect I've been getting since Thursday night, or yeah, I think it was Thursday night, I got the first email from a student. I'd only posted it a few hours before, and but there are some that start work really early on things, and that's good to see. Uh, but they've so far the questions have been technical Excel questions, and we get into those strange things of Excel. As you get deeper into it, there may be some interpretation questions you may have. And like we've done with assignments 1 and 2, the Wednesday class before, I've tried to deal with questions on that. And so I've arranged my teaching plan for Wednesday to be quite elastic. It can be short, it can be long. I can carry it over to next Monday. Um, but the I would ask that you try to do as much on assignment 3 as you can before Wednesday morning, and that that way any discussion of questions and how to do some things uh, we should be able to resolve reasonably well. If I cover stuff and you've not attempted the question, it may not make as much sense to you or help you as much. And my last note, I was just talking to the electrician. He's just left. His work's done, and I was afraid that he was going to cut off my internet for a short while doing some repairs. But we don't have to worry. He's done his work, and I have to do the connection afterwards. Oh no! Don't tell me. Once again, my slides have stopped. This is what happened to me just at 8:30. I got to this slide and I couldn't. Oh, nope, it's going now. Okay, it's just really slow. Okay, maybe it was this morning, but it was just really slow and I missed it. Seeing our future slides here, let me back up. Come on. Okay. So we started a problem a couple classes ago, but we've been trying to predict credit card balances using customer information. And towards the end of last class, or halfway through it, I started trying to discuss the process for building a model. And that I was recommending we start with a really simple model and then incrementally add stuff going forward. Probably what I had in pre. There it is. So, um, and we'd add them. So you start really simple because you want the outcome to be simple. And if you start simple, that often works that way. Add things to it if it helps. Don't add it if it's useless garbage. And it helps is if it makes the predictions better. So if performance improves, and our predictions will improve if it's giving us new information, new insight that we didn't have before. So when I tried adding limit to the model, it didn't get better because it turned out limit contained the same information that was in rating. If I knew rating, I knew limit. So it wasn't adding new variables, new information. So I shouldn't have even considered it. If I had a proper process for telling me, is this new stuff, I wouldn't have made that mistake. But even so, when I add some things, sometimes I end up adding some new information, but some of it I knew already. And that's when I've got two variables that are interconnected, that we call that multicollinearity, big fancy word that describes when you have two variables that are interconnected in some fashion. If you've looked at assignment 3, you've seen that it's a small data set. I would have liked it to be larger, but it took me days to put together the data that you've got. I want to use real data and, if possible, local data. Uh, and so what I did was I looked at house prices in Halifax in the last year, and I looked at only one neighborhood, at loosely the west end of Halifax, from Quinpool Road to Bears Road, from Connaught Avenue up to Robie Street, and looked at that block there where most of the housing stock is similar in age and type of structure and the like, 60 to 120 years old. Um, but it's a very popular area because it's close to downtown, close to the universities, hospitals, that type of thing. That the and that particular data set, it turned out there were only 86 homes sold in the last year. And so that's the data I pulled up and what it sold for, what they wanted for the property, how big was the house, how big was the land that it's sitting on, how many bedrooms, bathrooms, was it split into apartments or a single family dwelling, a whole bunch of different features of it. And you're going to find with a house data that we may have multicollinearity. I didn't actually dig too deep into it, and I suspect it's not too bad with the houses that are in that neighborhood. If you've got a bigger house, probably got more rooms in it, more bedrooms in it. What are you going to do with the extra space? And when you're getting bigger like that, it may have more bathrooms in it. That so once you know the size of the house, you may know insights about other features of the house. Multicollinearity problem. That I don't think it's too big a deal with that data set, but it could be because we would expect those variables to be interconnected. So it's going to be important if you were trying to predict, as you'll do in the assignment, you'll start on this one, and I may have it in assignment 4, do a little bit more on it, that how do we predict house prices? If we know the neighborhood, so that's an important feature, and it's the same loosely here. So bigger houses probably sell for more. Older homes maybe sell for less. Don't know. These are all pretty old. Maybe it's how many bathrooms, how big the land is. what are the features that drive up house price? Does it have a garage? So if I'm trying to explain things, that's when multicollinearity becomes an issue. We'll get to that later. So we're trying to incrementally improve it, and we're going to do it using trying to improve the predictions. You improve the predictions by trying to find an explanation of why you made a mistake before. So fix your mistakes, fix your errors. The errors are called residuals. So we're going to try to explain the residuals and look at the correlations. What we did last time was we looked at the correlations between the residuals and the variables we weren't using. So which ones seem to be correlated with our mistakes? Ones that had the biggest one we brought in. So we started with rating, then we brought in income, then we brought in age. Age wasn't too helpful. But beyond that, probably the other ones didn't add very much. So we went through that process of doing it. How do I go a bit further in studying those residuals, studying my mistakes? So if it's not adding these other numeric variables, what is it? Well, I wanted to keep my model simple, so I used only straight lines, linear functions. They're nice and simple. Maybe I should be using a curve. Okay, how do I know when I should use a curve? Residuals will tell me. We didn't use nominal variables, the categorical variables like gender and marital status and those sorts of things. That maybe I should be using those. How do I do that? They're not variables that go 1, 2, 3, 4, 5, 6. They aren't numeric types of things. And if I start getting into this, is there a way of deciding when to add variables? We've sort of done that already, but I want to go back and looking at that process aspect of how I'm building this and looking at, again, some of the issues that we've got. We'll run through this because we're going to bring to an end value estimation and multiple regression today. So let's get going on the residuals. That residuals is the mistakes we've made. What could not we not explain? And when we started doing residual analysis, we had this as being our first plot. So we had put rating in the model, made predictions. They weren't very good. Errors were pretty big. So we looked at how big those errors were as rating changed. And that we saw they could be quite big, like off by 800 up here, or minus 600 or 700 down here. A lot of big mistakes. But we also saw this line here. We had a particular problem with customers whose balance was 0. They could have ratings anywhere from about 100 up to about 300 or 400, and they all had balances of 0. So that's a pretty big, broad range of customers. All had 0 balances. Maybe we should look at balance separately or the zeros separately, but we're not going to do that. That's what we did last time. Was we then took the residuals and we found the correlation with the other variables and found that the income had a very good correlation with the residuals. And so we added into the model. And then we went back and looked at the residuals again. So this was what we had before with rating, before we put income in. And then this is after we put income in. And two things stand out in this plot. One is I've got a cluster that are floating up above the bulk of them. Now, they were sitting up here before, but I didn't really pay attention to them because I had other ones that were floating down below. But now they seem to be standing out. They're more prominent now than they were before. This very firm line that I had here is now fuzzier and it's steeper. It's over a smaller range, it seems, of ratings. I've got this sharp thing here. But look at it. It goes down, turns, goes up again. And then it sort of flattens out. So this looks like a curve. So I've got a curve and I've got outliers. Two problems. So let's look at the problems separately, one at a time. I can't deal with both at the same time. Oh, by the way, if I look at the other residual plot with income, I've got the bulk of them here centered around 0, but I've got a bunch that are floating up top. And you'll notice with the thick stuff here, it seems to be a little bit below 0. So I've got, here's 2 lines, same distance above and below. They're at 250 above and 250 below the line. And that's where most of them are, except for these odd ones. And this scatter, though, is just, it's not quite centered. It should be neatly centered around 0. And it's the outliers that are doing that. It's pushing the other guys down. So let me look at the curve bit. So this was the original scatter plot that we had credit rating or credit score and balance. We put a straight line through. And I did comment at one stage, I think, that this looks sort of like an S that's been pulled out. And it sort of, so I go flat, I go up, and then I sort of slow down again. So like an S curve. Or turned on its side, I'm going down, turning, and then sort of flattening out. Same type of thing. So it looks like a curve. How do I deal with this curve? Well, curves are hard to deal with. With straight lines, and you've got a straight line and you want to put a straight line through it, there is one good straight line that fits through it. That least squares line is the best line that'll fit through a straight line scatter. But if you got a curve, even just a U shape, I can give you lots of different curves where at least portion of that function goes and is U-shaped. So even if I had a sine curve that goes up and down and up and down, part of it is a U. And if I only use a piece of it, that describes a U. There are a lot of other ones that go down and up again. That this one goes down, up, and then it turns again. And in turning, I think of, in math, we talk of concavity. It's a strange term. It's U-shaped or dome-shaped, okay? And, or parts of it. So something that goes swooping like this is part of a U. Or if it goes zooming up like that is part of a U. Where something that curves this way is part of a dome. Even if it doesn't turn around and go down again, it looks like a piece of a dome. Okay? It's like a piece of the bottom of an egg, piece of the top of the egg. They have, one is concave up, one concave down. And if you want to build a curve, I'd recommend, again, keep it simple. Go for a really, really simple curve. So if you have just one bend to it, putting a square in there, having a quadratic, will give you that. So if you've got a function that a constant, the a plus bx plus cx squared or something like that, that quadratic function that you may have dealt with before, that's U's or domes. And they're nice and simple. That if you want it to turn a second time, you've got to go up to a cube. If you want to turn a third time, you've got to up to the power 4. They don't happen. At most, you're going to have 2 bends to a curve. And this is a really simple function to work with. Not perfect, can't fit everything, but it's a simple tool that we can use. And so here's a cubic polynomial. A polynomial is a function that has terms that have x and x squared and x cubed and x to the 4th, x to an integer, a whole number as a power. They're nice things to work with generally. And the terms are added together. So it's like a linear function with an intercept and a slope times a variable, and a slope times a squared variable, and a slope times a cubed variable. So it looks like a linear function. And I can build it by taking rating And then I could take rating and square it, and rating and cube it. So why don't I create two new variables, rating squared, rating cubed, and use those as new variables in my model? I created two new ones out of one old one. I've taken rating and made it into three separate variables. Well, there are some problems that come with this, that the numbers get big. Rating goes up to 1,000. So rating squared will go up to 1,000,000. Rating cubed will go up to 1,000,000,000. Those are really, really big numbers. I could write them out, but they're big. Okay? And think of the coefficient that goes in front of them. If um, if you're thinking of you know, if there was a lottery for $1 billion and you just won a little tiny piece of it, you're rich. Because even a small piece of $1 billion is a lot of money. Okay? The slope is how big a piece you're taking. Okay? Um, the coefficient, if your variable values are huge, your coefficients are generally really, really small. If your variables are super, super, super small, your coefficients are often quite big. They balance each other out, they multiply together. And if you want the numbers to be manageable and not get into bizarre figures, you should probably scale your data. And actually, our data was already scaled. That the income data, if you saw income being 90, that was actually $90,000. So we didn't have that huge number, 90,000 or 120,000 or 200,000 for income. We saw 90 or 120 or 200. They were manageable numbers. So they scaled them by expressing them in thousands. So I could scale these things by just shoving the decimal point over. That a more common approach for scaling that is generic and can apply to any type of variable, big numbers or small numbers, is called a z-score. A z-score is actually related to empirical rule. You'll see it come up in a statistics course. But it's a scaling device, and that's actually how it's used in statistics, although they don't tell you that. It's to scale things down to manageable size that's consistent, and it gets rid of your units of measurement. So it looks at your value, subtracts the average, mean value, divides by the standard deviation. And so a z-score can be +1, it can be -1. You can be above average or below average. And as to how much above or below average, we can have a generic measure by saying, well, you're 1 standard deviation above average or 2 standard deviations above average. That's what empirical rule is all about. Or 1 standard deviation below or 2 below. Z-scores are generally between -2 and +2 because most of our data is within 2 standard deviations of the mean. So our numbers don't get super big, they don't get super small, and they're centered around 0. And it doesn't matter what you're measuring. That description of 2 standard deviations above or below the mean applies to incomes, ratings, number of credit cards you have, what your age is, anything, any type of unit. And if we square them, if you were to take 2 and square it, you're going to get 4. Okay, so a big z-score becomes 4. How about -2? Square it, it becomes 4. So z-squared is probably between 0 and 4, maybe up to 9, but 9 or 10. Occasionally it gets bigger, but not by much. What about cubing it? Well, instead of getting up into the billions of ratings, I end up, if I cube it, to get maybe +8 as a high value. Or if my z is a -2, it goes down to -8. Remember, when you cube it, it keeps its sign, so it goes from minus to plus. But again, it doesn't get to be a super crazy number. They're manageable figures. And so z-scores are very, very common. Actually, many researchers take all their variables and transform them into z-scores. And they make every one of them being relative to what the average is. Sometimes a good practice. So what I did is I had income in my model and rating in my model and balance as to what I was predicting. And I went and created ZRAT. Let me see if I can get into this. I got so many tabs to this, I'm going to go crazy. I don't want that one. Here we go. And you see what I've got here. Whoops. So what I did, I had income, rating, and I created ZRAT. So I took the rating and if you can see this, I subtracted, I had calculated the average and I put it at the bottom of my spreadsheet. So I said, go subtract the average, and I calculated the standard deviation. It's down the bottom of my spreadsheet. And I divided through by that standard deviation. And so the average rating is, I think, is around 350. So I took 283, that's below average. So I subtracted 350, divided by the standard deviation, whatever it was. So this is below average. It ended up with a z-score of minus 0.46. The next one, 483, it's above average. So it ended up with a z-score that was bigger than 0, because it's bigger than above average. But it ended up being 0.827. So I scaled each of these. And if you look down, I got minus 0.46 plus 0.8. I get a 1, a 2, one that's close to 0, 1. They're all about the same. They don't, oh, here's one that's huge, 3.839. So some of them are odd, but most of them seem to be between minus 2 and plus 2. A lot of them are less than, or between minus 1 and plus 1. Okay. I then squared it. So minus 0.46 when squared becomes 0.21, becomes positive, minus times a minus. That when I cubed it, it became minus 0.1. So minus times a minus times a minus. So z cubed can be positive or negative. Z squared can only be positive. But these numbers, you'll see, are all manageable sorts of figures. I then took all of these variables, whoops, okay, those 4, and put them into my model to predict balance. Okay. And again, how do we do that? We go to data, data analysis, we go to regression, we look at, well, where is our y variable that I'm trying to predict? It's in column E, from E1, I don't know, you probably can't see this, E401. So it's in column E from the first row to the 401st row. There are 400 observations, and I've got 1 row for the labels up here. And then my x variables, they were in columns A through D, rows 1 through 401. I've got labels, so that these are not numbers up at the top. I put my output on the same sheet, and I'm going to ask for residuals and the residual plots. Okay, so I already did that, so I'm not going to do that again, and I'll just show you what I got. Okay, so when I did that, actually, let me go back to the PowerPoint because it shows better there. Whoops, not there. Here we go. This one shows you before and after. So this is the model where there's an intercept, income, and rating. Okay, and we had that issue with negative value for income minus 7.67. Income goes up, balance seems to go down, but that's because income and rating are changing at the same time. The model before had an R square of 87.5%, 0.875. So we look at that, and a standard error of 162, almost 163. So that means that my predictions of credit card balances frequently off by $163, sometimes off by $320, twice that amount. So not the greatest. Okay. Putting in a curve in here, well, my R square goes to 0.89, not a big improvement. So from 87, 88%, now up to 89%. I went up by about 1.5 points. Not very big improvement. I'm still an A level performance, but not an A plus. My standard error went from $163 to $150. Better, but it's not going to make or break me to, my predictions are $13 better than they were before. Not great. If I look at my model, the coefficients have changed. Okay. This isn't surprising because in a sense I've replaced rating with a curve with several variables. So it's going to go and affect everybody in different ways. And it's gone from 3.9 for rating to now 4.3. And it's got these other guys. Rating squared has a coefficient of 81. Rating cubed, a coefficient of minus 21. These are pretty big numbers compared to these guys. When looking at it, ask yourself, are you really that much better off? Now, it looks like the performance has improved a little bit. That did I need both the square and the cube to do that, or could one of them have been enough? Not quite sure. I normally suggest you look at standard error to give you clues about coefficients and whether or not they're giving you new information and useful information. And as I'm getting to having more variables, I've got to go back and see, did it mess up other variables along the way? So you'll notice back here, don't worry about the intercept that much. Look at income. Before I said it was minus 7.67, and it had a standard error of 0.38, or there, 0.37. So it suggested that the impact of income might be off by more or less by 0.38, or maybe twice that, okay, around 0.8 altogether. Well, what is it like now? It says the coefficient's minus 9, okay, and it could be off by 0.4 or maybe double that. So it's about the same as it was before. The accuracy is about the same. Coefficient value is different. What about rating? It said it could be off by 0.086, okay? Not by a lot, by less than 10 cents. What about now? 0.097. So my guess is that as rating goes up by 1 point, balance goes up by $4.31, but it might be off by 10 or 20 cents. It's still $4 and something, maybe $4.50. What about rating squared, rating cubed? Well, if the rating squared went up by 1, it's actually quite a big jump, balance will go up by $81.80. But it's not exact. It could be off by almost $10, maybe even $20. So this means the impact of rating squared going up by 1 isn't just $81, $82 here. It may only be $72 or $62. Maybe it's $92. Maybe it's $102. It's still going to go up by a big chunk. Maybe $60, maybe $100, but it's going to go up by a fair bit. Okay, so it's changing. It's definitely affecting balance. What about rating cubed? Well, if rating cubed goes up by 1, it says that balance will go down by $21, but it's got a standard error, margin of error of $3. So maybe it's not going down by 21. Maybe it's only going down by 18. Maybe only by $15. Maybe it's going to go down by $24, maybe by $27, by 21 plus or minus $6 maybe, or $3. It's still going to go down by a fair amount. So that's an important variable. So these variables are not making a huge improvement, but they are making a tangible improvement, and they are, I need, each one is adding some information. So rating squared is adding information, and rating cubed is adding information. That I've still got a multi-collinearity problem. I've still got that strange thing happening with income. Adding a curve generally doesn't fix those sorts of problems. It doesn't help you there. That it may improve how we're capturing rating information, but generally it does a nonlinear model, which is what we've got here, doesn't fix your multi-collinearity problem. So just be aware, it's still going to be there. How did it fix my residuals? Well, if I look at my residual plot before, this was the twisty thing, and this was the outliers that I've tried to fix. And here's what I've got now. Outliers are still there. I didn't fix outliers. I was trying to fix the twist. I wasn't trying to deal with that. So this is still here to deal with. What surprised me was the twistiness is still there. I thought I would have taken out more of that, but it doesn't seem that we've been able to fix that as well as I thought I might. But it is a bit better. It is flatter, so it's getting better. But um, maybe it's not the twistiness that was giving me bad predictions. Maybe it's these guys, these things that are floating up here. So one way of looking at this is like you've got two groups. You've got these customers and you've got these customers, and they seem to be different from each other. So if I'm looking at two groups, well, I have variables that talk of groups. I've got gender, males and females, and I've got married and single. I've got student and no student, and I also have ethnicity. That the customers, this was an American classification, that we've got uh, African Americans, Asians, and Caucasians. And this is what they would normally, oh, there it is. This is their typical classification. And frequently, US law requires a lot of reporting on gender and on ethnicity in these big categories. They Latin American is often added in as another category in here as well. But um, the uh, Asian, I think generally they don't differentiate in their broad classifications between um, what part of Asia. You know, are you South Asia, or if are you more East Asian, Chinese, Japanese, Korean sort of thing. And so there are other types of things in ethnicity. We could have a more granular split among this. But the we do have different categories, different groups here. So maybe the strange pattern that we're seeing in the residuals are because they have to do with these different groups that I've got here. And that, so we've taken account of their income and their rating already. This is stuff that's supposed to be left over. That, so be careful. Don't get absorbed in thinking, oh, well, students have lower incomes, so they would be different. I already took care of income. And students probably have trouble getting credit because they haven't had credit cards before, and so they don't have a big credit rating established. I've taken care of that. I've already done that. It's already reflected in it. That with some of the others, maybe you have reason to think of differences in income or credit rating based upon gender or marital status or the others. If the differences between those groups have to do with their income and their rating, we've already taken account of those. So this is over and above that. And so remember that this is because we're looking at residuals. Now, so what I could do and what I've done in Excel is I went back and with this one here that I had just done, okay, I asked for residuals, and this we talked about last day. So the first one, the predicted balance was $444, $444, and the actual was 333. So I ended up with a residual of minus 111. My forecast was 111 too high. So a negative residual means your forecast is too high. The actual was lower. But the next one, it turns out the actual, I think, was 900 or so, and my prediction was only 495, so my prediction was too low by $407. So I've got all these residuals. Grab all those things and paste them into a new sheet. And then go back to the beginning and find those variables at the beginning. I'll make sure I find my way back here. Here we had, oh, see, this doesn't want to let me zoom today. Okay. I can cheat though. I'll just change the font size. So I can take gender, student, married, ethnicity, grab those columns and paste them into your new sheet. So let me go over to my new sheet. Okay. And I'm going to get rid of this. This is from last class. And I'll show you how I'm going to do this. So I've got all of these guys in a new sheet. Let me zoom up to the top here. I got a bunch of plots here. You just don't look at them. We're reading ahead. Yep. Don't want to give you the answer right away. Anyway, this is all posted. This spreadsheet is in Top Hat. It's the Chapter 7 credit file. And again, it won't let me zoom. Well, it usually does, but it doesn't seem to want to let me do this today. So again, I'm just going to go and take these columns and make the font bigger so you can see what I've got here. Okay, so here's my residual here. And I've got male, I've got gender, student, married, and ethnicity. So let's make the columns wider. I can get away and doing that. There you go. You can see what I've got here. First off, I'm going to take the residuals and I'm going to look to see that the pattern is among the residuals. And I'm going to do, instead of a scatter chart, because I've got a categorical variable I'm going to be using, I'm going to use a box and whisker chart. So if they were two numeric ones, we do scatter charts. If it's a numeric one and the other variable's categorical, use the box and whisker. And it gives me this thing, and I'm going to move it up to the top. I hate it when they put these pictures down at the bottom here. Okay, and I'm going to make it bigger so we can see it. I'm going to change the format because I hate all that fill that's in there. Oh, it's all right, wrong thing. There we go. And I'm going to make my lines a lot thicker. Big fat lines. Okay, so now you can see my chart. It suggests in terms of the residuals, most are clustered in a fairly narrow range. that, and so you can maybe see what these things look like. There. Okay, now I'm getting a chart I can read. So actually most of them are, here's 0. That's where this spot is right there. Okay. That's, and most of the residuals, or that middle block of 50%, most of it is below 0 actually, that they're on the negative side. And they seem to be clustered a little bit low because I got all of these outliers way up here. So in the residual plots that I showed you before, like, I didn't show you there, but here was the one with rating. Most of my residuals are clustered around 0, and a few are way, way, way up high. So now this is the way it is. So I don't have that horizontal scale. I've just compressed everything and put it into a box and whisker chart. So I've got this odd bunch here. Who are they? So what I can do is in design, go over to select data, go over here to edit, and it says, well, what do I want to put as a label here? And I'm going to go and pick gender. So I'm just going to go zip all the way down this column. You can type in the label, what they are, but click OK. Puts the male, female, male, female. Click OK. And I have to go back up so you can see my picture. And look at my picture. There we go. So here's for, and everything's too small. Let's make these bigger. So males, females. Okay. Most of the values are really the same for both groups. These, if I ignore the outliers, these 2 box and whisker charts look the same. There's nothing, and they look fairly symmetrical, almost bell-shaped. You know, bulk in the middle, the whiskers on the 2 ends are about the same size. So this is really nice, except I've got a huge number of outliers for both. Something's wrong. Okay, so let's go back here. Let's select data again. I'm not going to pick that. Suppose I picked ethnicity. Zip down this column and see how these guys are different from each other. Click OK. So it's got Caucasian, Asian, 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 Caucasian, and so on. Oops. Oh dear. Spinning. Not happy. I don't like it when it does that. Ugh. Hello. It's starting Excel all over again. Okay. We lost it. So I'm going to have to give you the answer by looking here. Okay. I'll be back to my slides again. Don't tell me my slides are stuck. So I did that, and I brought up different ones. That was the process. Here are all the charts together. So jumping to the solution. And just to remind you, as you saw, Excel crapped out on me. It does that. Excel sometimes does strange things. It's not your fault. If you look at gender, marital status, ethnicity, you end up with 2 or 3 box plots that look really the same with outliers. So the outliers belong to all 3 ethnicities, to both married and singles, that to both males and females. But when we split it on student, you find here are the outliers. Okay, the ones that are sitting way up high, all those dots, are all students. Everybody else is down here. And there is a little bit of overlap. Okay, so there are some students, I guess, that are inside these male and female whiskers here up at the top, but not many of them. That bulk of them are these guys here. And so that suggests that I should take into account student status in building my model. So if you didn't want one, at the very end of the course, you should have done binary variables, that variables that take on only two values, yes, no type variables. We use them generally in selection decisions. Yes, we do this. No, we don't do that. So in making those yes, no decisions, that we use binary variables a lot. And with gender, marital status, and student, those are all binary variables. So I can set this up to go and do it in that sort of fashion. With ethnicity, it's more complicated. And if we have time at the end of class, I'll show you how it's done. It's not critical, but we end up having to create additional binary variables. So if it's a binary variable, we can incorporate it into our regression model. If it takes on many values, like ethnicity or what program you're in if you're a student, or where you're from if you're a student, where there are many categories, we have to create more variables that are each binary. So we can only use binary variables, but we may have to address our issue by creating a lot of them. But we'll get to that if we have time. So what I do is I build the model in this fashion. I have balance as an intercept plus beta 1 times income, beta 2 times rating, rating squared, the rating cubed, and this last variable, beta 4 times a new variable I created, student 01. And to create that, I did the opposite of what we did at the start of the course. The start of the course, we might have had a variable that was 0 if you're not a student, 1 if you are a student. And we did it like we did with gender, where it was 0 for male, 1 for female. And we converted those to words because it was easier to read. Now we're going to take words and convert them to numbers so we can put them in a formula. Okay? If we want a formula, we need numbers. If you want to read it, better with words. So I've created a variable that's a 0, 1. How? That, well, first I'll get to, well, I did it with an if statement. I'll show you it in a second. But if you're thinking about what does it mean, if you've done binary variables before, you'll know if the binary variable is 0, then it just disappears. So if this value here for student 01 is 0, 0 times anything is still 0. So this just disappears. If you're not a student, this doesn't fit you. If you're not a student, your model is just these pieces, the top section. If you are a student, then I get a 1 times beta 4. So I'll end up getting this base case plus beta 4. It reflects that if you're a student, how much more or less do students carry on their credit card than other people? Okay, so it gives me an indication of how much different they are as a fixed number, because either you're a student or you're not a student. I'm not saying all students are going to be the same, but on average, again, we're always looking at averages. On average, how different is their balance? So I used an if statement. I copied the words in, and then I put in another column, and I put in if this value equals yes, then I'll give it a 1. If it's not a yes, I'll give it a 0. Notice if you're doing this recoding, the words have to be in quotation marks. Okay? That because I have to tell it it's text. So if F2 equals yes, then I'll give it a value of 1. And if it's not equal to yes, I'll give it a value of 0. Okay? And this way, I can then incorporate these things in. All right. Now, let's go and see what happens when we do that. So this created my new, here are my X values now, from A up to column E, and I got balance in column G. And I fit the regression model. And is Excel back to life again? Did it recover? Seems to be a problem. I'll deal with that later. We're going to just work from the PowerPoint output. Okay. So I fit the model, and this is the results I get. This is what I had before I put student in. This is after I put student in there. Before, my R square was 89%. Not bad. Now it's 96.8%. That's pretty close to 1, pretty close to 100%. So that's, in terms of R square, that's a nice improvement. You can see it a lot more in the standard error. I went from being predictions that were off by $150 to now being off by $83. So I've almost cut my error in half. My predictions are much, much better than they were previously. That what happened with my model? Well, it is interesting. My coefficients didn't change. They changed a bit, but not a lot. So minus 661 to minus 687, 9.17, 9.41, 4.3, 4.3, 81, 78, minus 21, minus 18. So they're similar. There's not a big shift in them. If you look at their standard errors, okay, it's interesting that they're cut in half. I've estimated the impact of income or rating squared or rating cubed, or the intercept for that matter, with far less error than I did before. Standard error tells me how accurate are these coefficients, because they're not perfect. They're off by a little bit. And now I've cut the error in it in half. So not only did I cut this overall error in half, I cut the error in my estimates in half. And then I've got the student variable. It says if you're a student, on average, you owe $417 more than if you're not a student. So even though I've taken into account your credit rating and everything else, so if you're, if you could imagine, if this was our data and about our class and what you've got on credit cards, if you were a, I'm saying that, your income last year was $7,400 and your credit rating is such and such, or you were a lobster fisherman and you fished for half the year and then went to school for half the year, and your income last year was $68,000 and your credit rating is something else. So very different students in terms of income, but you're a student in both cases. I'd expect on average you owe $400 more on your credit card. But if I was comparing two people that were very, very different in terms of income and the like, but one was a student than the other, then I'd say that the student was owing $400 more than the person that was not a student. This is the impact of just being a student, regardless of what your income is. Okay? So it I know students will have different income, but this suggests that they're not paying off the balances, whereas someone else that's not a student will pay off their balance, regardless of what their income is. And my estimate's not going to be off by more than about $14, maybe double that, maybe $28. So it's still around $400. So it's not, this is a fairly good estimate. If I look at my residual plots, notice that the income one, it's got a blob, but it's pretty concentrated around zero, balanced above and below. I've got a few stragglers, some low income people that look strange. With rating, I've still got the little bit of the S here, it looks like, but it's still pretty flat around zero. And I've got then this little cluster of 5 people down here. Even if I looked at the students, that it's among students that I've got the outlier still. So these are ones that I'm still not able to estimate all that accurately. A negative residual means my forecast is too high. These might be the students that pay off their balance, and the rest of them aren't paying them off. Not quite sure, but um, so it is among the students. I've got a group of maybe 5 low-income students that I'm having trouble with, but the rest of them I'm doing fairly well with. So to run through what I've got here, my forecasts are much better. My error is cut dramatically. I still have some odd ones that I've got, but overall my performance looks to be much, much better than it was before. That in terms of causal analysis, I can talk specifically about a student. Notice that the other parts of my model didn't change much. So student isn't correlated really with income and rating and that type of stuff. That if it was, it probably would have disrupted the other coefficients a lot more. That So I can be doing causal analysis and talking specifically about students separate from income and rating. That, as I said, the standard error of the coefficients, it's much, much smaller, suggesting not only taking account of students has improved my overall forecast, it's also improved my ability to separate out the impacts of the other variables. That doesn't always happen, but when it does, it really means I've got extra sorts of improvements on the explanation side, on the causal analysis side, which is really helpful. That Now a lot of what I've done is very crude. In a stats course, you'll do it in a more formal fashion. But to be honest, I think if you can understand this, you understand the important aspects of multiple regression. Getting into the other stuff gets into finer details that you probably don't need and you wouldn't use in explaining to an audience why they should believe your forecast. That you're going to snow them under with technical jargon. Managers want you to keep it simple, and that's what I've been trying to focus on here. So what have we learned through all of this? We started out trying to predict credit card balances and understand maybe why some balances were high, some were low. So we're looking at both value estimation and causal analysis as our objectives. That we did find that ratings were a good indicator. Credit limits didn't tell us anything new. That because they were both interconnected, the limits seemed to be based upon the ratings. We discovered multicollinearity problems. Income and ratings, I can't separate. I can't talk about one without talking about the other. That's going to be a problem. This problem is commonplace. Don't be surprised. You can be disappointed, but not surprised. That if my main focus is on value estimation, don't worry about it. If your main goal was to do causal analysis, you're out of luck. Sorry, can't help you. That in general, in building a model, the process you're going through, keep it simple. So simple in terms of the number of variables, simple in terms of the form of the function. A linear function is easy to work with, easy to explain. Um, you know, one point increase a rating, my balance goes up by $2.57. Those sorts of things it's nice to be able to talk in those terms and explain them that way. And curves are very, very hard to explain. Like now that I've got rating cubed and rating squared, it's going to make it really hard to explain. That if you've got to have curves, again, keep it simple. Use polynomials; they're the simplest functions. But I'd recommend that you scale variables. that it's try not to get it too messy in terms of numbers that you're dealing with. You want your numbers to be something manageable. You don't like numbers that are too big, and you don't want ones with a whole bunch of 0.00000. Those are frustrating to deal with. Most of us like numbers that are 15, 4, 38.2, 121. Those are nice numbers. I can work with them. Add your variables incrementally. Add them only if your model improves. If the model is doing okay, you can probably stop. You don't need to perfect it. You know, don't be a perfectionist necessarily, unless there's a real benefit to being a perfectionist. In terms of how to add them, residual plots are your best source of information of what to try next. They're what you haven't explained. And this is a really important message in general in improving any type of work you're doing. That we learn by, most of us, by trial and error. So if you're going to learn by trial and error, it means you got to look at the error. Just don't say, mistake again, and just go try again. Doing the same thing over and over again with no changes, you're going to make the same mistake. Why did you make the mistake? What can you learn from that so that the next time you'll do better at it? And that diagnosis in regression is by looking at residuals. In other types of things, maybe you need someone to watch you so that you can see what you're doing wrong. You need someone to prod you with questions or something. But you have to go and drill in and find out where are the mistakes happening. And there are strategies for doing that. In our case, we'd probably be looking at plots of variables against the residuals. Or if you're lazy and you just want to add another one, look at the correlation. We did a quickie correlation table, looked at that and found which was the one that seemed to add the most information. Because we're going to be adding them in a straight line. And you're probably going to pick the one with the highest linear correlation. So that's a good strategy. But there are some things, as we've seen today, that correlation wouldn't tell us, but a plot would tell us. Okay? In terms of sequence, generally add the one, be greedy. It isn't always the best strategy, but it works in a lot of problems. So when you're trying to improve things, if you could only do one thing, what would the one thing be to give you the biggest bang for your buck, the biggest improvement? That we call a greedy strategy. And usually it works fairly well. Sometimes it leads you down a rabbit hole, leads you down a bad path, but most of the time it works well. You used it, though you didn't know it, when you did Quant 1 in linear programming. The Simplex method searches for a solution. It looks for an answer, then says, if I could change only one thing in this answer, what should I change? And move to another one. If you did graphical method, it was moving to corners. If I was moving from one corner to another, don't jump across space. Go along an edge to a neighboring corner. Which one would that be? And it turns out if you use that strategy and keep going until there's no move that's better, it'll get you the best answer. It works for regression reasonably well, but it's not perfect. That should you ever delete them? We haven't talked about this, and it didn't come up in ours, but it can. Suppose you started out, I put in variable A, and I added B, because it made it better. Great. And both A and B they're important. They may be interconnected, but they're doing fine. I added C, and hey, it's a little bit better. Okay, that's great. And C did add that extra bit of information. Okay, just like I added rating squared and rating cubed. Suppose I go and add variable D. And once I added D, it turned out that the standard error for A became really big, or the coefficient became really small relative to the standard error. And it may well be that A is not important anymore, but it was the most important one. I put it in first. It should stay, shouldn't it? No, it turns out if I've got B, C, and D, I don't need A anymore. The information that was in A is incorporated in B, C, and D, and so I can throw it out. So we can get cases where adding in a new variable actually creates a multicollinearity problem such that one of the variables that I had in before, I should now throw away. And if that standard error relative to the coefficient is big, throwing it away will not make your model worse. You'll find your standard error will stay the same. Your R squared will stay approximately the same. Okay? So throwing something away isn't necessarily bad. It's not going to make your model worse. It's just that you've been adding things and now you don't need to keep the old stuff anymore. It was valuable then, but it's like cleaning out your attic of stuff that was valuable maybe sometime in years ago, but you don't need it anymore. You can throw it away. And that's what's happening here. So that is a good practice, is to check to see, do I need to keep everything? But that's beyond our class here. When should you stop? When you're satisfied with the performance, when you're finding the performance just isn't, you can't come up with a better way. You can't think of anything to improve it. Stop. Okay. This one, I got as probably as far as I should go, except for those 5 cases. Maybe I should look into them. But for the most part, I think I'm okay, and I'm not going to kill myself. There are a lot of debates about this. I've given you a strategy. There's no one best method. When we get into material from chapter 8, we're going to be looking at problems where there are many, many different methods, and there is no best method. There's no dominant methods. That with regression in building, there is no best strategy. I've given you one that I use as a problem-solving strategy in general, not just for regression. I keep my models simple. I keep my solutions, when possible, simple. I add things in only if I think I'm improving things, and I stop when I can't get any better. Not complicated. If I have to have a formula, I keep it a simple one. I like straight lines, easy to explain, easy to calculate. There is a problem, though. Statisticians, at least when I was trained, would never, ever consider doing what I've just told you all about. What I'm telling you was like living with the devil. You're just, everything I've just told you is all wrong. That I was told you should never do any of the things I just did. And there were reasons for that. A lot of it had to do with the amount of data that we had. Today we've got lots of data. So what happens is that you may end up overfitting. You may have found a model that is just perfect, but it's only perfect for your data set. It won't work anywhere else. So what you should do, and data miners are aware of this, of overfitting. If I've got a lot of data, in your assignment 3, there's only a little bit. I couldn't do this with 86 observations. But if I had 800, I'd probably take 200, randomly select them, and I'd put them away and not look at them. Take 600 of them and build a nice, good model, one that I was happy with. And then I would simulate how would it perform in practice by using the 200 cases that I didn't know about. So I'd predict the house prices for those 200 homes and see, well, how good a job did I do on the prediction with the model I built based upon the other 600. We're going to talk about that later when we get to evaluation. But um, I think we've addressed the statistician's worry. So I've tried to keep a simple process. I've said it several times to you, and I'm not going to repeat it. I'm over time. What we're going to get into next is classification models. And that's like turning it around and saying, if I gave you a customer's balance and their credit rating, could you tell me if they were a student? So I'm going to try to predict a binary variable based upon other variables. So this is very different. It's prediction again, But instead of predicting a number, I'm going to predict a category. And it's a hard problem to do. And there are a lot of different ways people have thought of doing this. But I'm sorry, I've gone too long. And if you're really curious about how to handle categorical variables where there's 3 or 4 or 5 categories, I'm more than happy to show you how to do it. But I think you've got more than enough to deal with already. Class is over. Start work on assignment 3, and we'll talk about it on Wednesday. Take care. Keep safe. Class gone.